It was kind of fun to stay at the
Okay, let me look at my calendar. After class? Okay.
Yeah. I like how all that.
Yes.
I have a good question.
Sure.
On those last ones, it's like 2 terminal switches but multiple circuit terminals.
Yeah.
When we write out our answer,
Yeah.
because I'm not,
That looks beautiful.
I'm just trying it
Yeah.
a bunch of times, but I'm not like mathematically thinking about it rigorously.
Yeah.
Is it okay just to put an answer for these without an explanation?
Sure. Like, I mean,
I don't know if you're going to get credit because I don't really have an explanation of how I got here.
I know it would be hard to give an explanation of how you got there.
Right,
Yeah.
so that's why.
No, I think this is fine because it's easy for us when we're grading it, in a sense, to verify.
Okay.
Yeah.
That's okay. I just wanted to make sure because everything else I can explain.
Yeah.
Is,
Okay, that makes sense.
The thing he built was like
like, are you saying like connect here to here with an X? I mean,
I have the odometer. It's displayed to the LCD. It's 506. Which don't work. No. I just got to this comment trying to figure out how to swipe the LCD.
I like how you emails.
Figure that out later.
I don't want to be frustrated like that's how it is. That's how it's going to be. What do you hear that? I've been wanting to for a while, but it's I was taught by a teacher. It's always a bad class.
because I'm taking 52 as well. Yeah, if you can't, well,
other than 4.
Oh, okay. And then you
Because I'm going to go pretty.
oh yeah, it's the same thing. You have to
Just try all 160
Okay, so I would hazard a guess that there will be some questions about the homework. So please. And it is actually helpful for you to ask questions and for me to answer them in front of the class. So because many of you probably have identical questions. Yes, Jordan.
You sent an email regarding the grading for some questions, so how much explanation
Yeah.
code?
I know that this is a very good question because, in a sense, nobody's commented on this, but the email that I sent may have sounded contradictory in terms of the directions that I gave. So the TA who's grading this, I'm grading some of it, he's grading some of it, he is drowning, as you can imagine. He's extremely diligent, but it doesn't look like it, but there's just over 100 students in the class with Unite students. And each homework is taking him more than an hour to grade. And you won't be surprised at that. But he's really struggling. And the email that I sent was, in a sense, I just copied what he had emailed me as suggestions. And he's quite right that he would like a little bit more in the way of explanation for some of the answers that are coming in. Meaning, for a problem where you sat down and you wrote some code, just writing C-attached code makes it very burdensome on the grader to try to interpret what's going on. Because the grader, first of all, has to figure out what your program is computing, try to look at some of the printouts of what it's computing, try to figure out if it's correct. But that said, life is short. It's shorter for me than for anyone else in the class. And I made the mistake when I was a student of spending way too much time not preparing beautifully crafted, beautifully written homework assignments, but I was paranoid. I was paranoid that the grader wouldn't understand what I wrote and I wouldn't get the points for it. So I would over-explain, over-justify the answers. I would be afraid that if I just wrote down an answer that was obviously correct, I wouldn't get full points for it because I hadn't shown how I derived it. In some cases, that's true, but now sitting on the other side of the fence with grading, oftentimes it is quite apparent when the student has the correct answer and you need less information than a good student might think. So I don't know what I'm saying here. I'm going all over the place. So perhaps, Jordan, can you ask for the second homework, specific questions on...
Yeah, just like what, just for what a small paragraph just explaining what the program does.
Yes.
Would that be sufficient?
Yes. So that's what I would emphasize. For those of you who are submitting programs, always submit a paragraph. Now, don't submit 5 rambling pages of incomprehensible text. You don't have to worry about beautiful writing, but just make the paragraph as informative as possible and keep it at that. Just an explanation. First of all, explain whether your program is complete and whether it works, or if you're handing in, because students for homework 1, some of you handed in code that didn't even compile or wasn't even complete, and you just handed in C-attached code. And so then it's hard for the grader to interpret it. So emphasize whether your program works or not, what it has computed, whether you think it shows a correct solution to the problem. And I'd say keep it, short paragraph. Okay, ask more. So what else?
I guess to use your program that you sent us,
Yeah.
Do we need to compile that in Linux
Oh.
or in a Linux environment? Because I've had issues trying to compile it within Windows.
Correct. So I sent an email last night with the Windows version. Did all of you get that? It's annoying because there was a zip file and Gmail blocked zip files. I'll try again. But
Post it to your wiki page.
even better. So I'll just post it to a wiki page so you guys can download it. So short answer is the code that I sent you will compile on a Mac or a Linux machine. To get it to compile on a Windows machine, the changes are trivial, specifically with Visual Studio. The changes are trivial. It's basically a header file that you have to change. The header files are different.
Okay.
It's just, and it has to do with the time.
Yeah, instead was it system/time, so just time.h or something like that?
I think that you have to add a prefix in front of systime.h for the correct path in Visual Studio. So I'll try to do that immediately because you guys only have till Friday. For those of you, and I guess you're supposed to use this program, that particular homework problem where I ask you to run the program to analyze lambda is the easiest problem that you'll get in this course. There's nothing to it. You just run it and plot the results from running it 10 times. But the intent is to show you how the program works and what it can show on a model like lambda. Okay. Other questions? Some questions regarding the switches. Yes, Seamus.
So this is more of administrative, but
Yeah.
the previous homework was like due at midnight, but since you want us to turn in a paper copy, I'm guessing this one's due by class time.
Yeah, let's make this one due by class time. So let's make this one due at 2:30 on Friday. But one important administrative note, and again, I have to email you guys this, don't print out your code this time, for those of you who have developed code. Instead, you should upload it, and I'll send you easy, simple directions on where to upload your code. So hand in a paper copy of your solutions. Any code, you'll upload it. I'll give you directions on how to do it. Okay. Questions? Yes?
What if our code and solutions are in the same document?
That's fine. Well,
I can upload it too.
you can upload it too, but in that case, give us a printout. Because as we discovered last time, with 100 plus, as I said, 100 plus emails coming in, it took me all day to print them. So just because each one was, it would take a few minutes to print. You know, it wasn't just send PDFs. People sent 4 or 5 files, and I had to, sort them. Yeah. So is that if you've already made a document, then please print it. Yeah. Yes.
I do have a question in regards to code.
Yeah.
If we run, if we had something to get pretty good stat numbers on problem 1, where
Yeah.
we ran like a million, loop of a million, 1,000 times.
Yeah.
Can we put that result in our homework and then decrease the loops for use so that it doesn't sit there running for a while?
Yes, please. Of course. That's
But
a.
the results aren't going to be exactly the same.
Sure. So in general, because this homework assignment involves code that runs for many iterations, we're not going to deduct points if you hand in a solution that's not accurate to 15 decimal places. I would say that I should have given you proper guidance for each problem, how accurate it is. But if we can see that your solution is correct, I don't really care how many decimal places. So I would say as a ballpark, aim for 2. Aim for 2 decimal places. So for the lambda problem, 0.81, 0.43, 0.26, accurate to 2 decimal places is good enough. That should correspond, depending upon the problem, to perhaps 1,000 or 10,000 trajectories in general of simulation. That's good enough. Yeah. Okay, some questions on the switches. Yes?
How much do we need to show for simplifying the switches?
Yeah, so I just got that question from John. It's a good question. For this one, basically nothing. Because it, in
Basically nothing.
That means you can just program it, do it on the computer, and just simplify the whole switching network, and you can do it in 2 seconds. For number 3, is that what you're talking about, or the last one? For 4,
but what computer program do you use?
you can just plug the Boolean expression into Wolfram Alpha, and you can get the simplified thing, and you can factor out a variable, and you can have 9 switches.
Okay. So you just told the class how to do that one, but that's fine.
I figured that wouldn't be worth full credit, though. I mean,
It would.
that would be. I figured that would. Like, you need to show your Boolean algebra theories and what you're doing.
No.
I have 3 pages.
So I stand by what I said for homework 1, that you don't have to invent, this is using legal jargon, work product. So if you arrived at a solution, you don't have to invent a justification for how you arrived at it. And so what a student, John, was asking was, he said he played around with the switches a lot, sketching on toilet paper, different solutions, until he had one in front. He didn't say that. But until he had one that worked. And then he said, well, okay, how do I justify how I got this? Well, if you got it just by sketching, then just give the final answer. And in particular for this one, for the grader, it's not difficult to look at your solution and verify that it's correct. and count the number of switches. So for the entire problem on switching ones, in a sense, your derivations of how you simplified it are not that interesting to us. There you can pretty much provide the final solutions. Yeah? Is that okay? But so for Wolfram, like, I mean, it'll do Boolean simplification. My program symbol will do the same, but it won't get you down to the extra credit ones.
It's close enough where you can just factor it or
Okay.
do De Morgan's twice, factor something out, and you're basically there.
That sounds good to me. So that's what I want you guys to do. Okay.
I should have known that. You know,
And I hope you guys don't begrudge me. As I pointed out, many of you went ahead and you solved the first two problems by writing your own code. And then after I assigned the assignment, I gave you my code, Aaliyah, which could, of course, be used to solve problems 1 and 2. I hope you don't begrudge that. I appreciate if you went through the exercise of trying to figure out how to do stochastic simulation yourself. So I hope you're not angry about that. Yes, some other questions. Rowan.
So for the switching, or for the not the chemical reaction.
Yeah.
When they say demonstrate that it works.
Yeah, that's a good question.
What exactly do you expect?
So it was unfortunate the way I phrased it. I said either prove that your solution works mathematically or demonstrate it through simulation. The word proof sounds ominous. It sounds like you have to. So all I meant by that was provide some justification or explanation for why you think that your solution works.
So just like words are fine?
Words are fine. Even just a suggestion to you, because it's surprisingly, there can be surprisingly subtle issues. I would suggest that your solution for the computing the log base 2 of, so you have to compute log base 2 of, what was it? Of y raised to the power, what did I do?
well, it's 2 to the log 2x. 2 to the power of
Oh, there you go.
Yes, there you go.
Okay. So this problem, where first you have to compute the logarithm and then you had to raise it to a power. You have a bunch of reactions that you think implements this. What I would suggest is take the code Aaliyah that I sent and type in your reactions. It's easy. Just type in your reactions as, if you have x goes to a plus b, type in x1 goes to a1 goes to b1 with a rate, if you had a rate of 1,000 here, 1,000. So just type in your reactions, run Aaliyah. And if you supply initial values of x, it should compute the right answer. So it's a way to verify. That, to me, would be what I'm looking for in terms of showing that your result works by simulation.
Do you have to provide that Aaliyah code? Or?
No. Just say I use the code that you submitted. But if you don't want to run Aaliyah, if you don't want to run programs, then at least provide the sort of explanation that I provided in class when I stepped through chemical reaction networks, arguing that something is correct. And as you guys may have noticed, that just taking, I hope that you guys can appreciate just taking the set of reactions that I provided for logarithms and those for exponentiation and just sticking them together, that's not sufficient. The problem is that if you're doing two separate computations, you need the results of the first computation to be complete before you start computing the second one. And so you need some mechanism. And that's what I'm looking for in this problem. Any further questions in that room?
And just another question.
Yeah.
Another problem is like when we looked at Claude Shannon's master thesis.
Pardon me?
Claude Shannon's
Yeah.
thesis. It's like when he does the switching stuff, it seems like his plus and times are.
Oh, yeah, I thought I mentioned that. So Claude Shannon, it's an interesting historical note that he uses the opposite convention for everything. So he uses
Ones and zeros were opposite. So.
He uses 0 to be closed. He uses 1 to be open. So that's the opposite of the modern convention. And as a result of that, then for multiplication, this corresponds to the or in his case, and addition to the and. So What's interesting is he originated this whole field, this topic, and yet the modern convention is the opposite. So when reading the paper, that can throw you a bit. Was that your question?
Yeah, so
Yeah.
like what I was saying is like, are all his rules still valid?
They are. You
For,
just
like modern conventions too?
They are. So you just have to change every 0 to a 1, and you have to change every multiplication to an addition and vice versa, and everything is valid. Yeah.
But do you have to change that in his rules as well?
Yes. So, well, you can go with his, like it's just notation. So you can stick with his notation, or you can change it.
Right.
But if you mix, then you'll get errors. Yeah. Yeah. Okay. Now let's turn to the topic of binary decision diagrams. So I'll get into what I hope is going to be quite an enjoyable topic in a second. It'll be what I call chimpanzee computation. But I want to, and the model for chimpanzee computation, which is my own particular label for it, is in a sense a model of a graphical model for a data structure. By a graphical model, I mean we use nodes and we use edges to represent a function. But before doing that, staying in line with the theme of the course, I'll present an idea for how we can use such a graphical model to structure the information contained in a set of chemical reactions. The motivation here would be for binary decision diagrams. Everybody recalls what binary decision diagrams are. It's the game of pachinko, where you start with a marble, you drop it at the top. When it encounters a variable, it goes left or it goes right. And based upon the variables that it encounters, it falls out of the bottom into a bucket. If it falls into the 0 bucket, the function evaluates to 0. If it falls into the 1 bucket, the function evaluates to 1. So the feature of a binary decision diagram is it's a data structure that captures, or that encodes, I'm using a lot of jargon here, that represents a function, potentially a large function, a function that if you were to write out as a truth table would take up an enormous amount of memory or space, but because you're able to compact the binary decision diagram, it can take up much less space, so it can be a very efficient data structure. And it's the intuition here, for what it's worth, as to why the binary decision diagram will be much more compact than a truth table. It all starts from the bottom. The bottom, you've got 2 buckets. You've got the 0 bucket and the 1 bucket. Initially, if you had the full binary tree, then you'd have a lot of buckets at the bottom. You'd have a lot of 0 buckets and a lot of 1 buckets. But you slide all the 0 buckets on top of each other, you slide all the 1 buckets on top of each other until you have a single 0 bucket and a single 1 bucket. Then as a result of that, you're able to slide some of the nodes above it on top of each other, merge some of the nodes, do more sliding. So the compaction starts at the bottom, and you start compacting it until you have, hopefully, a more efficient representation. So this data structure, it works because, this is intuition, that the input space is very large. So the number of possible 0, 1 assignments you could make to, let's say, 1,000 variables is large. But the final answer, when you evaluate it, is just a yes-no type of evaluation, just 0 or 1. And so in those situations, we can use this category of efficient data structure. So the question is, let's say we're given a set of chemical reactions, like the kind you're considering on the homework. Given such a set of chemical reactions, it would seem in general that characterizing it is not a yes-no type of exercise. But in some cases, it might be. So based upon what you're seeing on homework 2, I'm forgetting all your names. Scott? Scott. What would be a yes-no type of characterization that you had to do on homework 2? Let's stick to chemical reactions, so the problems with chemical reactions. So for chemical reactions, which of the problems with chemical reactions could kind of be cast as a yes-no type of exercise?
The one with lambda?
Yeah. So for the lambda, the virus one, there, what you're looking for is, does it go into one state, lysis, or does it go into the other, lysogeny? It's kind of a yes-no. But what I had you compute instead was probabilities, so it's more subtle. But you could imagine that, and I'll show you some examples of types of questions that we can ask about chemical reaction networks that are yes-no type of problems. It was a while ago that I presented this idea to a group of synthetic biologists, and I never followed up on what I'm about to show you, but this really resonated with them. They said, when we're trying to do a computational analysis, we're nearly always interested in something that has either a yes-no type of answer to it, or at least qualitatively does. And so what you're interested in is, does your system work? Does it produce ethanol from cellulose or not? Sometimes you're interested in how much it produces, at what rate it produces, but often it has that qualitative feature. So we're interested in a system where we might be going from many, many input possibilities to simple yes-no possibilities. Okay, so any ideas of, think of, let's see what comes next. I think the fonts are off and we know this stuff. We know what chemical reactions are, and here the fonts are off. But imagine that we had a set of reactions. A plus 2B goes to 2C. B plus C goes to 2A. A plus C goes to 2B. Any idea of how we could package this in the form of a decision diagram? Just some thoughts. Because it's different here. We don't, what are the variables? And, you know, it seems like a very different problem, but I'd like to get your minds going. Jason? So, Jason, no. Jake? No? What could be, so instead of the variable x1, what might you look at? Or x1, x2. How about the types, A, B, and C? And then what would you be looking at? Because each type, A, B, C, doesn't have a specific value. It has... I'll return to this slide because this is what I wanted to explain. Sorry. Okay, so let me begin to step you through it. Suppose that to get the process going, that we have three possible starting states for our system. Imagine that our system has three molecular types, A, B, C, and we have three possible starting states. We can start in a state where we have 4 of A, 7 of B, and 5 of C, 3, 5, 7, or 3, 4, 5. So each state is one possible initial configuration. Let me ask you this. How can we encode these three states in a decision diagram? What would it look like? Perhaps I'm prodding you guys to solve a problem that isn't so interesting to solve. So here is how we might do it. Well, if you look at the values that I've listed for A, they can be 4 or they can be 3. So those are the two possibilities. For B, it can be 7, 5, 4. For C, it can be 5, 7, 5. So here is a decision diagram that encodes those three states. But so it needs a little bit of justification. How does it encode those three states? Or what does it encode about those three states? Ryan? Or what's your name?
Jared,
Jared.
any path you follow is one of the states?
Yeah. And so if you start at S, then any path that you follow is a state. So here, in the data structure, I'm actually losing the information of which state I'm in. I'm just representing, I'll call it the set of reachable states. So this will be the set of states that I could be in. So here, this is part of the premise. I'm going to relax the assumption that I care about what state I'm in, and I'm just going to track the information globally of what state I could be in, assuming that I could be in one of these three states. So how to interpret this? Well, you could imagine that from each node, like A, all possible, I don't know what, this is supposed to be a 7, not a 77. There's animation, just got shifted. So every other integer value is simply a no condition. And so, from each possible variable or each state, you have a number of integers, and each one is a valid path to follow, and together it encodes the full set of states. Meaning any path that you follow, as Jared said, that takes us all the way to the bottom, is a state that it could be in. All right. So now, Jared, why might I want to track the set of reachable states? Or what could I do next? Because we'll have a set of reactions that corresponds to our problem. And this might be, I have 3 states to begin with, but then I may want to figure out what happens next.
I'm not sure what you're asking for tracking.
Yeah. Okay. So here is the idea. It's very much, within the field where people study data structures of decision diagrams, they often talk about state reachability. So that's jargon. But in this category of problem, the state is simply a possible assignment of values to the variables. That's a state. And you're interested in whether or not your system can reach a given state, if there is some path that takes you there. Why might you be interested in this? Well, like with the lambda versus lysogeny problem, you might be interested from this initial starting state, can I reach lysis or can I reach lysogeny? If you're into metabolic engineering, you're interested from these initial states, can I reach a state where something happens? So the premise is that we've encoded a set of states that we can be in, and now we want to track the evolution of the system, meaning if reactions fire and quantities change, what states can I be in next? So we're in some initial set of states, that's the state before, and then reaction is going to fire. So if reaction R1 fires, we'll be in a new set of states, or we can be in a new set of states. Reaction 2 fires, we can be in a new set of states. Then we're in the state after. So how can we do this with the decision diagram that I showed with the tree, or what's the metaphor? This looked like some kind of monster with hanging arms. So, yeah, Alex.
Do you just encode all of the state afters from your initial state? Like, say, reaction 1 fires, and then you have so much A, so much B, so much C, and you just put those in a line going down the list, and then you have another line for the second reaction and another line for the third reaction.
Yeah, I think that's exactly what it is. So suppose this is our set of states, and it was 3 states that we had encoded before. Now there's a reaction R1 that fires. So A plus 2B goes to 2C. So if R1 fires, this means we have 1 less of A, 2 less of B, and 2 less of C. So it means that the set of reachable states that we can be in would be, if R1 fires, simply the arithmetic. From every integer on the value of A, deduct 1. For B, add 2. Deduct 2. For C, add 2. So this is the optometrist game. 4, 3, subtract 1 from A, 2 from B, add 2 to C. And you get what's on the right-hand side. So this is in itself not useful because I had a tree that represented a bunch of states and just a trivial transformation that gives me a new tree. But this is the tree that I get only if reaction R1 fired. I could also have R2 firing or R3 firing. So Alex, what do I do for R2 and R3? I do the same thing. I think I have the slides for that. Okay, that's another tree. So now I had one tree, this is a big gnarly bush, and now I have 3 gnarly bushes. But what do I do with those 3 gnarly bushes?
I don't know. Chop them down, sell them for lumber.
Yeah, bushes aren't so useful for lumber. They're good for... So any ideas? You can combine them. So why can't you combine them in essentially using the merging techniques that we had before? So here, it was a lot to write on one slide, but if I've got S1 or S2 or S3, so here, what I'm encoding is the set of states that we could be in. So let me back up. So keep in mind this slide. We could be in a set of states before, and then 3 reactions can happen. So now for each reaction, we can be in 3 separate states, collections of states. What we have to do is merge 3 separate collections of states into one new collection of states. And this will be work computationally, but it won't be that much work. Like, I mean, if you guys had to do it for this example, you would take the 3 bushes and combine them into this one bigger bush. So now from A, we can be in 3, 2, 4, and 5. And then for B, we can be in 5, 9, 2, 6, 3, 7, 3, 4, 6, those conditions. But you get the idea that it's just a straightforward process of merging when we can. So what is the point of all of this? Alex? So I'm growing shrubs. I'm combining shrubs, and I'm maintaining a collection of shrubs. But what can I do with this shrub that I have? So it's actually, I don't know how effective it is in the case of chemical reactions. I'd actually be interested if someone, because I never pursued this idea, of actually looking at writing code that would perform this merging on the states and seeing for a simple set of chemical reactions how well you can maintain the set of reachable states. Because if you think of it, your code in homework 2, the examples that I gave you for the first problem, they were really trivial. They were like this. They were just A plus 2B goes to 2C, just 3 little reactions like that. And so there, you start with small values like 3, 3, 3. And what happens is, sometimes A goes up, sometimes B goes down. The number of reachable states that you can be in, after all, is limited. And the whole exercise is to track how the set of reachable states you can be in, how it evolves over time, and whether or not you hit an ending condition. This is something that I think could be just encoded into a relatively small data structure, and this would solve the problem of how to compute an answer as opposed to just doing a random simulation of it. And the reason why you can do this is, I don't know if I'll explain this properly, but in a sense, what we're doing is we're performing the computation when you're, so think of simulation on a set of chemical reactions. So you're in some initial state, 3, 3, 3. When you do the simulation, you go to some other state. You go to 4, 6, 7. Thought there was a monster stumbling through the room. You guys are all too young to remember this, but there was a great sequence of commercials when I was a kid for Kool-Aid, where there's this character who's actually a huge Kool-Aid pitcher, a pitcher of liquid, and he comes busting through a brick wall, and that was the commercial for Kool-Aid. You've seen it? But this means that ad campaign continued past the 1980s, which is hilarious. All right, so you follow a given trajectory, which is you start at a given node, and then you follow some trajectory down. That, if you're doing this as random simulation, you're choosing at random what happens and following one path. In order to estimate the result, you have to do this randomly many, many times, because each time, it gives you a sample of what could happen. But with this kind of idea, what you're doing is you're saying, from this initial state, let's look at all the possible states I could be in. I was in this one state, and after one state, I can be in 3 states. But you encode the 3 possible states you could be in one data structure. And so after one step, you take all the possibilities and you compact them down into essentially one meta state that you're remembering. And then, again, from each of these, there are a bunch of possibilities, and they can take you to even more states. But since you've compacted this down to one meta state, you do the computation on the next set of states you can do to compute the next meta state on a data structure that's growing in size, but you're doing one computation. So you go from S to a bunch of possibilities to T. And then from T, you go through a bunch of possibilities to U, and so forth. So you're doing a lot of work each time to compute the meta state. But what you're doing is instead of 3 times 3 times 3 times 3, so instead of 3 to the power of the number of steps, in a sense, you're doing a linear number of computations on a data structure that's growing. So the trade-off is how big is that data structure? Is it growing out of control so that each step, so instead of doing 3 times 3 times 3, you're just doing this kind of step. But at each step, is the work exploding or not? And that depends upon the problem here. But for small integer values and for a simple set of rules, likely the amount of work you're doing is not exploding. And so what you're doing is a huge savings over the amount of work that you're doing over here. Does this make sense? I don't know how interesting it is in the case of chemical reactions. And in particular, so what have we lost here? We've lost a huge amount of information this way. Probabilities. So previously, what you were doing in homework 2, the entire name of the game was computing how likely it is to get to a particular area here. Here we're losing all of that information. So we're doing a weaker type of analysis. But suppose that you weren't interested in probabilities. Suppose that you were interested in the following sort of questions. So yes, no questions. So you were interested in the question, a given particular state, let's say this is a state that's really important to you as the synthetic biologist or the metabolic engineer. So a state where you have some assignment of the values that's important to you. And you want to know, well, is there some way that I can get there within 100 steps? That's a yes-no question. And it's one that potentially you could answer very easily with a decision diagram type of approach, whereas answering it by an exhaustive analysis might take much more work. But you could also ask, suppose that I'm in a particular state. Is some other state reachable from that initial state without ever going through an intermediate state? That can be interesting. Imagine as a metabolic engineer, you want to know if you can get to a state where you're efficiently producing your biomass without having gone through the state where your machinery explodes, that kind of scenario. Or more typically, you want to ask, is a given state never reachable? And that's interesting. So how could you answer a question C3? Because the never reachable part seems difficult in general to answer the never part because you just keep going, and how do you answer the never part? So any ideas? Has anyone studied decision diagrams in the context of circuit design? Think about it for a second. How could you answer the never part?
Eventually, if the metastate doesn't grow.
Wonderful. Yeah.
Then that means that you've reached all possible things.
Yeah. Terrific, Jake. So that's exactly the intuition that I was looking for. So here, the metastate is the set of states that are reachable, so after a given step. If you do another reaction, the metastate, in a sense, now includes more information. And if you keep performing that operation, but then let's say you go through this full iteration, it's like turning a wheel, but nothing happens. Your data structure hasn't changed. It means that now your data structure simply includes all reachable states, and no further reactions will get you anywhere else. So this type of data structure can be immensely powerful, not for answering questions in the positive, How many steps can it take to reach a given state? But rather for proving that you can never reach a state. In other words, for encoding in your shrub the information of all the states you could reach and proving that you can't exclude one. The trade-off here is, of course, in your shrub, you've lost all information about specific states. It's just the full set of states are in there. But it can be very powerful for answering questions in the negative. OK. I'll toy around with this, but perhaps for homework 3, it might be fun to have you guys work with this type of data structure for encoding the set of states. But what I'd like to do now is to switch to, depends how well I set it up, but what I think is a very fun topic. OK, so let me switch gears. Related to decision diagrams, but specific to our simian cousins. I gave you a teaser of this, I think. I did it very poorly. I did it right at the beginning of the first lecture. I gave you a teaser of this topic, declaring this to be chimpanzee computation. So here is the problem that I'd like to set up, and the slides aren't terrific here. Suppose that you have the following problem. You'd like to compute a function of many variables. For the sake of arguments, let's always stick with either, for the n variables, let's stick with 10,024. So roughly 1,000 variables, that's 2 to the power 10. But imagine that you wanted to compute a function of 1,024 variables. Suppose that function that you wanted to compute is are more than half of them 1. That's called the majority function. You can imagine that's a really useful function. You've got a lot of variables, and you want to return a value of 1 if more than half the variables are 1. If they're all 1, that's fine. If 750 of them are 1, that's fine. If 512 of them are 1, that's still 1. But if 511 are 1 or less, then it's 0. Everybody gets that. So it's a counting problem. And you would say, well, that's really easy. Just look at the assignments of your variables, go through them one by one, and count the number of ones that you see. That's fine. You could solve the problem very easily. But suppose that in order to perform this task, you want to do it with extremely limited memory. So in this case, I'll insult, in evolutionary terms, our furry friends, chimpanzees, and declare that the chimpanzee model here, the chimpanzee has extremely limited memory. What do I mean by memory? Well, when you're counting, you have to write things down or remember a number in your head. And to count up to 512, you need at least 9 bits of memory, because you can't count up to 512 if you don't have 9 bits of memory. Everybody agrees with that? 2 to the 9 is 512. So suppose you had much less. Suppose you had 3 bits of memory. That means that you as the creature, you can only count from 0 to 7. That's it. You can count up to 7, and then you can wrap around back to 0. That's all you can remember. How can you solve this problem? Okay. I'll let you guys think about it for a minute. I always have this problem with energy drinks.
Well, I mean, if it's on
But
Team
yeah,
TV,
so
it's not.
I'm sure I'm just gonna intentionally.
I got,
Because I'm probably responsible.
Yes, yes, we'll take files.
Definitely, of course. But on the right side,
It's just like
You know, if it's a one, you add one.
Okay, any ideas? So Alex, what's your idea?
Great, you're done, cool. So you tell the monkey to,
Monkeys are not apes, so this is an ape.
you tell the chimpanzee
Yeah.
to set the buckets so that it has a pattern going, 0, 1, 0, 1, 0, 1, 0, 1. And
But,
just-
sorry to I interrupt,
so
but
it's
what do you mean he
got
has...
rocks and buckets, right? 1 is there's a rock in the bucket, 0, there's no rock.
Let's go for grapes. There's a grape in a bucket or no
There's
grape?
a grape.
Yeah.
Okay. So you set up grape, no grape, grape, no grape, grape, no grape, and it just goes along until it reaches the end. And like find the point when it can no longer establish that pattern. And if there are more grapes at the end of that pattern, like there's a whole bunch of ones, then hey, we've hit the majority. If there's a whole bunch of zeros or no grapes, then we don't have the majority.
So I like this, but you're bending the rules. And we're not going to bend the rules at all. So I think what you're suggesting, so let me set this up. And so the game that I'm not playing here, so this is infuriating, you know, these kind of mind puzzles where you have to solve an impossible problem and then the person asking it actually bends the rules in some unexpected way to have you solve it. I don't know what's an example here. We're not going to do this. This is legitimate. So here's the problem. Imagine that you've got 1,024 buckets. And the input to the problem is some distribution of grape versus no grape in each bucket. That's the input. So contrary to what Alex was suggesting, the chimpanzee can't go around and move grapes. Or we can't move the grapes. That's the input. So that's what's decided. The only thing the chimpanzee can do is he can wander up and down the line as much as he wants, looking in each bucket. He can look in each bucket, look to see if there's a grape or not. He can move to the next bucket. He can look to see if there's a grape or not. He can go to any bucket in the list, and he can look to see if there's a grape or not. But if he sees a grape or not, in his head, he can only be in 8 states. So he can say, okay, well, I was initially in state 0. I see a grape in this particular bucket, in bucket 256. So now I'll go to state 1, state 2. But somehow you have to count up to 512, even though you can only count up to 8. So is that a little bit more specific?
You mean you can remember only 8 buckets at a time?
He can't remember 8 buckets. He can just remember a state that he's in. So, because imagine that he's actually a computer. So he's a computer that initially is in state 0. And you're allowed to specify instructions. And the instruction might be, look in this particular bucket. If you're in state 0 and there's a grape in this bucket, then go to state 3. If there's no grape in this bucket, then go to state 5. But the number of states that you can bounce around in, there's only 8 of those. Yeah, Roy.
Say that one possibility is you could just, if there is a grape, you add 1, and if there's no grape, you subtract 1.
Yeah, but what if...
But that would take up too much.
But and so that's a good suggestion. But suppose that you get all the grapes up front, you get 510 grapes, and then the other buckets have none. You can't even count that high. Yes, Scott.
Could you walk down the bucket of grapes and look in each bucket, and if there is a grape, make your count or whatever represent odd, and if there is no grape,
Yeah.
it represent even.
I know. When I've presented this before, people have had that idea. And that's good. But odd and even. So explain a bit more. I don't think this works. Like, I mean, how do you...
So you're trying to count the total number of grapes, right?
Yeah.
So if there is a grape, then you change the counter. If there's not, you don't.
but change the counter between odd and even, just an up-down?
1, 0.
1, 0. So you're flipping a switch.
Yeah.
But the thing is, what if you happen to look in 510 buckets and you always see a grape? So you've switched the switch a whole bunch of times up and down. And then afterwards, you have no idea how many grapes you've seen. You've just seen an even number. Then whether or not you have a majority or not, so what if you're at 513 or 511, 512? Even an odd doesn't get you anywhere here. Yeah. But it goes to what I think is the heart of the problem. Like, I mean, the answer is a yes-no type of problem. But to collect the information to make that yes-no problem, it seems like you need more memory. There's just no way to compact it down. And yet there is. And in here, we're not going to play any funny games with probabilities. Maybe some of you might say, well, let's just look at a bucket at random, and if we look at enough buckets, then we'll get an estimate and play some game like that. We're not. There is a way to count to a very large number without much memory, and it has to do with permutation. So, okay, I'll begin to explain it to you, but basically we're going to just arrange. It turns out we need 5 objects. And then we're going to shuffle the 5 objects around. And by shuffling the 5 objects around, magically, we can count to a very high number. There's, in a sense, mathematical magic here, and this is why I like this topic so much. So let me begin to set it up as a binary decision diagram problem. I guess I could try to prompt you guys a bit. Does anybody have any initial idea how... Okay, let's make this a little bit more explicit. I'm not changing the rules at all. It's exactly the rules that I specified before, where we have 10,024 buckets. The input to the problem is some external, the zookeeper. He goes and he places grape or no grape in each bucket. That's the input. That will change, of course, every time we evaluate the function. But when it comes to evaluating the function, there's grape or no grape in each bucket. That's set. And even before this starts, even before we enter the zoo, we're going to assemble a set of instruction cards. The instruction cards, they're printed on paper, and we don't get to write any scratch notes or pad on them. Each instruction card is printed ahead of time. The instruction cards, we have a stack of them. We don't get to shuffle the instruction cards. We don't get to do anything. But here's what each instruction card says. Each instruction card is an instruction for the chimpanzee that tells him what to do. And it tells them what to do in the following sense. It says, first of all, go to a specific bucket. It's allowed to specify any bucket you want. So it can say, go to bucket 253. That's the first bit of the information. The next bit of the information is, of course, look in that bucket and see if there's a grape or no grape. The next part of the information is a following. It can be like a lookup table. It can be, pretend the chimpanzee is in one of 8 possible states. So state 1 through 8. On the instruction card, there will be, if we have 8 possible states, 16 lines. So just twice the number of states. It'll be, if there's no grape, and if you're in state 1, it tells you what state to go to. If there's no grape, and you're in state 2, it tells you what state to go to. If there's no grape, and you're in state 3, and so forth. That's the first 8. Instructions. The next 8 instructions are, if there is a grape and you're in state S1, then what state to go to, and so forth. Does everybody agree with that? So, but these are fixed ahead of time. You don't get to shuffle the instruction cards. You don't get to specify on a given instruction card what to go to some other instruction card. There's no branch operations here. And that's the problem that we have to set up. So, okay. How could this correspond to a decision diagram? How would you set this up as a decision diagram? Pardon me?
A really big one.
A really big, well, no. It'll be, in fact, it'll be small, and it'll be simply the length of the number of instruction cards we have. And so, just to specify a little further to pique your interest, I'm not playing because computer scientists can be really annoying by this. They can specify a problem like this, and then it turns out it can be solved with a stack of instruction cards. But the number of instruction cards you need would be 2 to the power 1,000. And then actually, if you think about it really hard, if you're allowed to have 2 to the power 1,000 instruction cards, or 2 to the 24 instruction cards, it's pretty easy to solve this problem. But 2 to the 1,000 is an unimaginably large number. In fact, we can solve this problem with a very small number of instruction cards, less than 1 million. 1 million is a small number. Okay, but so go ahead, Alex. So why did you say it would be a big binary decision diagram?
Because we have a whole bunch of key inputs, which is the grapes in the bucket.
Uh-huh.
You have to get your tree to a yes/no decision, right? So he has a card to look at one state, and then based on that, he goes to a different state, and then he looks that up, and you build a long tree from that.
Mm-hmm. Yep, agreed. So, but don't worry about how it computes the solution, because there's going to be, as I said, I shouldn't preface it this way. It's only magic because, how to put this?
It's only magic because you haven't played this yet.
Yeah, or it's only magic because I don't understand why it allows us to solve this problem. I can follow all the steps, I'll explain them to you, but there's something magical about permutations, about shuffling things around, and shuffling things around allows you to compute, to count, without ever knowing what you're counting. Okay, but to move things along a little bit, because we haven't even started the meat of it, here is, and this is not a solution. This is just the template. This is just a way of translating the problem with chimpanzees and buckets and grapes and instruction cards into a data structure. So the way we're going to set this up is, and here, for the sake of brevity, I go to only 4 states instead of 8. In fact, the solution is going to require 5. 5 is the magic number. That you can't solve this with less than 5 states, but you can compute the majority of any number of variables. Forget about 1,000. You can compute the majority of 1 million states with a 1 million variables with only 5 states. So the brain of the chimpanzee only has to remember only needs 5 states. But here, this will take a moment for me to explain what's going on. It's an ordinary decision diagram like the one we've seen, where we start at a given point S, we visit a variable, that's like going to a bucket. We look in the bucket, there's either grape or no grape. And so depending upon grape or no grape, we either go left or right, solid line versus dashed line. We go solid line to some other state, some other column, dashed line to some column. Some column for dashed, some column for solid. So that's in a given state, if there's no grape, you go one place. If there's a grape, you go some other place. And we just continue doing that, but we can only bounce around between 4 states in this example. And then at the very end, we magically land in the 0 bucket or the 1 bucket, and this will tell us majority is 0 or majority is 1. So again, it says nothing about the magic, but it's just translating this into a decision diagram. So is it clear to everybody? Can someone perhaps paraphrase better than me? I want to make sure everybody's on the right page. So Ryan, the instruction cards and the columns, what's going on here?
I'm pretty unsure. I mean, each
Okay.
instruction card is for a different column, right? Like depending on which one you're at, you can have a different.
Yeah, but does that make sense? Or so what part are you unsure about? Help me.
No, I guess it does make sense.
Yeah, okay.
You can have different instructions depending on where you are.
Yeah. So I think what confuses people always, I showed here, is that, for the first, you start at a given state, just because we're going to initialize we're going to boot up the chimpanzee into state 1. And so that top little triangle part is irrelevant. I just included it here for simplicity. But in fact, this is a proper decision diagram. But after 4 rows, we just have a solid column. But the way it works in terms of the metaphor of instruction cards is we start in state S1, and the instruction card is the row. So the instruction card is just what's included in the row. The instruction card, you notice that in each row, we always look at the same variable. So that's what I said. The instruction cards go to a particular bucket. Looking in the bucket is, so we're in a given node of the decision diagrams, we're always bouncing around the decision diagram. If we're in a given node like this one, x2, the instruction card told us to go to x2. Then we're going to look in the x2 bucket and see if there's grape or no grape. If there is a grape, we're going to go to state s3. If there's no grape, we're going to stay in state s2. The way I've drawn it here above, you can see the 0, no grape, means always stay in the same state. And grape means go to some other state. The solution won't always have that property, but it'll often have that property. But does everybody see how this just corresponds? So as we descend the decision diagram, the chimpanzee's mental state is just bouncing from column to column to column to column to column, depending upon what the instruction card says and whether there's grape or no grape. All right. So, yes, John.
I am a little confused
Good.
about this. I'm just confused that if you can have like 1 million instruction cards, why we're worried about memory in the first place. I'm just like kind of confused.
Yeah.
The problem being set up if we have all this space for instructions. I'm just a little confused.
Yeah, absolutely. Okay, let me answer. Your confusion is not about what I'm saying, but why the hell I'm saying all of this.
Yeah.
Okay, let me try to answer that because this will pique your interest. So, suppose that you wanted to represent a function like the majority function. So you wanted to build the circuit that actually computes the majority function. Okay, let me explain this a bit better. The majority function, in a sense, is a good example to motivate this because it's easy to understand. But it's a function that if you had to build a circuit to compute the majority function, you'd simply build a counter. You'd simply build a counter with however many bits that you needed. And so your question is an excellent question. But bear with me. In the following sense. I'm struggling a bit to come up with a good explanation here. The short answer is bear with me a bit, and I think you'll see that what I'm presenting here is not just a brain teaser of an idea that has no practical implications. I really think this could have important research implications in the sense that you can represent not just majority function, but any function of this number of variables with this data structure. And imagine that this data structure was actually a binary decision diagram type structure. You've fully encoded the function. This is a much smaller encoding than any other encoding. That in general, 1 million is actually small for the size of a graph that encodes a function of 1,024 variables. The truth table to it is 2 to the 1024. This is simply 1 million. You see what I mean? But I should provide a better explanation than that. Yeah, just bear with me a little bit. Because what I'm interested in is, suppose that we would actually build circuits, not data structures, that would compute this way. So just as a sideline, I think I've asked this question before in class. Has anyone taken a course, the course here in computer architecture? What can you say? So, Alex, what is pipelining?
It takes a while to do an instruction, so you start working on one, and like you have to do a certain set of things. to fully complete your instruction. So you start one, and then it does the first thing, and that moves on to the second thing. But since the first part of the instruction, or the first part that handles instructions isn't doing anything anymore, you put in a new instruction, and then they just kind of move down the line until it reaches the end and it's fully completed. So you just keep sticking in instructions, and it's working on 7 instructions at the same time, or 6, or however long your pipeline is.
Yeah. Okay, very good. I don't know if I can give a better explanation than that, but the concept is, exactly to repeat what Alex was saying, in computer architecture, in order to get your computer to operate at a very high clock speed, computing many, many instructions per second, to compute each instruction takes a certain number of steps. You have to fetch the data, you have to perform the addition, you have to take the result and store it back in memory. The idea is that you can compute the instruction in steps. There might be, let's say, 10 different steps. And the instruction, as you're computing it, you go through, imagine like an assembly line where you have to do the next task, the next task, the next task. You have your car move through the assembly line, and you don't wait for your full car to come out at the end of the assembly line before having the next car move into the assembly line. You simply keep the pipe full. You keep the assembly line full. So, John, to pique your interest here, this data structure is incredibly narrow. And it's long, or it's narrow, but it's tall. But it's not that tall. 1 million isn't actually that tall. And it's extremely regular. So here, if we wanted to design circuits to compute functions, then in general, those circuits will be quite irregularly shaped. Here, the contention is we would just have, it'll actually be 5 states wide and about 1 million states long to compute functions of 10 variables at a time. And there is the potential that we could seriously pipeline this. So the computation of the first function is we bounce around through the variables. And immediately, the computation of the next function is following just one step behind. So we've got a pipe that's full of instructions, each of which is just coming out at a very rapid clip. And so that's where I'm going with this idea in terms of its implications. I don't know if that makes sense. But let's, yeah? Okay. But let's continue with what I hope is the brain teaser aspect of this. I've told you that here's the setup, instruction cards, and chimpanzees. But it's from the brain teaser aspect, it still seems impossible. So even if you're allowed, even if you accept this framework, with a relatively small number of instruction cards, recall that you're looking at a function of 1,024 variables. And at each step as you go down, all you're remembering is one of, I should have really drawn this for 5, one of 5 possible states. So it's still the same problem that we were considering before. You, like Scott was saying, okay, you may think even and odd, you may think I'm going to toggle back and forth. But the point is that if you can remember just where you're at, in terms of one of 5 possible states, there seems no way that you can count up to 512. But the way that we're going to do this is through the magic of permutations. Okay, well, I always go slower than expected. So let me introduce permutations. Okay, so first, I'll just barely have time to introduce it. How is each row a permutation? Or what is a permutation? Let's start with that. So, Jared, what's a permutation?
There's a better explanation of variation within a set. I don't know how to expand on it right now.
Okay. But I'm sure that you know what it is. So if I have objects like star, smiley face, frowny face, and what else? And square. 4 objects. Let's go for 5 objects in circle. Here, I've got a left to right ordering. A permutation is just a shuffling of these. So I might put star here, I might put circle here, and I might leave these guys the same. So a permutation, this is a synonym, is a shuffling. So the order is important. When you permute things, you change the order. Same number of objects. So how does the binary decision diagram correspond to a permutation? Jared? So I've got 1, 2, 3, 4, and then as I've written it here, what happens next?
They either stay in the same spot
Yeah.
or switch to a different.
Right. Or, so the term that I'm giving this tentatively as a research topic is I call these conditional permutation structures. Because each row, each step between rows is a permutation, is a shuffling. So I've got 1, 2, 3, 4. And if the value of the variable is 1, I do a shuffle, one shuffle. If the value of the variable is 0, I do a different shuffle. So the solid lines give me a shuffle. The dashed lines give me a different shuffle. In this particular case, the dashed lines going straight down correspond to the shuffle that is don't shuffle. And the solid lines correspond to shuffle. But does everybody see that? And so it's just a different way of casting the problem that previously we had a decision diagram where we've got a variable. Based upon variable, we bounce around. But here, if we confine ourselves to a structure that has a fixed number of columns, and then each row accessing the same variable, that means that the step between rows each time will correspond to a conditional permutation. If the variable is 1, shuffle it in one way. If it's 0, shuffle it in another way. Okay, just bear with me for a second here. So the xi equals 0 is the 1, 2, 3, 4 stays the same. The variable xi equals 1 is the 1 goes to 4, 2 goes to 3, 3 goes to 2, 4 goes to 1. So what I'm talking about here is how I reorder the objects. The object that was in position 1, I'm going to put it in position 4, 2 and 3, 3 and 2, 4 and 1. That's what I'm showing here in this step. Okay, so just introduce a bit of the notation that I'll be using on Friday. Instead of writing it out this way, first of all, we're going to restrict ourselves. So, no, this doesn't have to do with the notation. But just as it turns out, we're going to restrict ourselves to cyclic permutation. So quickly, what's a cyclic permutation? Jake? Pardon me?
It comes back to whichever state we started from.
Yeah, so a cyclic permutation intuitively is one, well, it's a permutation, so it's just a shuffling. But it's one in which if you follow, so this is a very loose description of it, but it works. If I follow the sequence, 1 goes to 4, and then I look where 4 goes to, if 4 goes to 2, and then 2 goes to 3, and 3 goes to 1. If I follow that kind of sequence, 1 goes to X goes to Y, Y goes to Z, it means I visit all the items. The previous permutation that I had was not cyclic. So this permutation, I had 1 goes to 4, 4 goes to 1, 2 goes to 3, and 3 goes to 2. So it means in terms of how I shuffled the objects, there were 2 islands. I shuffled the 1 and the 4, and I shuffled the 2 and the 3. A cyclic permutation is one in which there are no islands. I do a shuffle where if I follow what goes to what, I go through every object. It's a restricted class of permutations, cyclic permutations. And there's no computational reason, but it just turns out that the explanation that I'll give works, it simplifies things if we talk about cyclic permutations. Okay, let's stop there. I'm really sorry. I'm so dysfunctional when it comes.
Yeah.
At least a good question.
My afternoon is actually kind of busy. Could we meet as late